With over 83 million developers worldwide, Git is not only a must-have skill in your resume, but is also a crucial part in the entire DevOps lifecycle. The goal of this tutorial is to help you get started with Git and make you comfortable using it. Although this is not an exclusive course, you'll understand some of the important Git concepts which will help you start using Git and will also help you with interviews. In this tutorial, we're going to talk about some of the basics of Git versus GitHub. We'll understand what is a version control system, installation steps, some of the important Git commands, branches, and their practical use cases, etc. And of course, with some great examples. We would even go a step further to actually deep dive and understand how Git operates under the hood. We talk about Git objects like Blob, tree, etc., which will eventually help you understand some of the advanced Git concepts. I hope you're excited to learn Git, so without any further delay, let's get started with Git. Why do we need version control system? Meet Mr. Bob, who is an investment advisor, and due to all the amazing work he's doing, his client base has increased significantly over time, and so he sees a need to have his own personal website. So Bob had envisioned a website of his own, and Bob being a non-technical guy, he thought of taking help from a freelancer to get the job done. So he met Sundar, who is a freelancer, and explained him everything what he's expecting in his website and gave the deadline as 24th of February, which happens to be his birthday. To which Sundar agreed and started working on the project. Inside Sundar's computer, Sundar had created this folder called Investment App, inside which he created all these files which would make that website. After a few days of work, Sundar had finally finished working on creating the website. He tested it. He also hosted it on a hosting provider or on a cloud service provider, got the application up and running, and shown it to Bob. Bob was quite impressed with the work done by Sundar, and so now he decided to add a couple of more features into his website. And he gave the deadline as 20th of February, to which Sundar once again had accepted the deal and started working on those additional features. And once again, Sundar had added all those features, hosted it on a hosting provider, got the website up and running, and shown it to Bob. But this time, however, Bob was not completely satisfied with the work. Even though the latest features introduced after 24th of February were working fine, the features that were working earlier seemed to have broken or are not working as expected. So Bob had explained the same to Sundar and asked him to undo all the new changes and bring back the application to what it was on 24th of February. To which Sundar hesitantly accepted, but unfortunately for Sundar, it's not going to be an easy task to undo all those changes, because there's a lot of new code introduced after 24th of February, and the code has scattered across multiple files. It's really hard for Sundar to recollect each and every line of code that was introduced and undo all those changes. However, Sundar wanted to accept the deal to keep the client happy. After a lot of sleepless nights and after a lot of frustration and a lot of testing, Sundar finally got the job done. However, this time, Sundar missed the Bob's deadline, and Bob was wondering why it took Sundar a couple of weeks just to undo the changes, while it only took him a few days to create the entire website. This has resulted in Bob being not satisfied. And soon Sundar started to see similar kind of issues with some of his other clients as well. They were complaining that some of the features were not working as expected, which had worked earlier. And so they either wanted to get them fixed or they want to go back to previous versions of their web applications which were working fine. So Sundar gave it a thought and finally came up with a genius idea which has somewhat solved this problem. We'll talk about it in just a while. So what Sundar had started to notice is that he didn't have backup of his client websites. If he had a backup of their websites, he will have opportunity to either go back to previous working version of their website or at least analyze the problem by comparing one version with the other. So Sundar came up with a brilliant idea to sort of solve this problem. What he started to do now is, for example, let's consider the investment app that we were talking about. Sundar creates a folder called investment app V1 and 14th March, which is the date on which this project was delivered to customer. And then assume that Bob had asked him to introduce a couple of new features. This time Sundar is not going to make any changes in this version of the project. Instead, is going to make a copy of that project, name it as V2, and introduce all the new features. And similarly, if Bob were to ask Sundar to add even more features, he's going to make a copy of the latest version of his project, name it as V3 for instance, and then make all the necessary changes, so on and so forth. So every time he introduces a new feature or introduces a huge chunk of code, he's just simply going to copy the folder or the project and make necessary changes. So this time, again, let's assume the same case where Bob was complaining that version V4 is not working as expected and that he wished to go back to version V3, which was working fine. So Sundar doesn't have to take the effort of reverting all the changes. He could just remove the V4 folder from the server and replace it with V3 working version of Bob's website. Or if Bob had insisted him to fix the bug, Sundar can actually compare the files between V3 and V4 using a comparing software like Beyond Compare for instance, pinpoint exactly the changes that were newly introduced, analyze the problem, and fix the problem. While this has somewhat solved the problem, Sundar started to realize that this is taking up more memory than needed. Because Sundar is not only making a copy of all the files that he had modified, but also the files that he never touched. So this is going to take up a lot of space and it's becoming really hard for Sundar to manage. So Sundar came up with a much better idea, which is actually to create versions of the files inside the project. What do I mean by that? So assume that you once again have a project like this with all these files. Now, of course, in this case, I named them as HTML, but this could be any file. This could be an image file, CSS file, JavaScript file, Java file, whatever. For the sake of this example, assume that we have all these files. Now assume that Sundar is introducing a new feature which has something to do with file B and file C. So instead of creating a copy of the entire folder, Sundar is going to make a copy of the latest version of these two files. So he's going to make a copy of file B and file C, introduce all the code required for feature 1. And if you were to introduce another feature, and this time assume that the changes needs to go in file A and file C, Sundar is going to simply make a copy of latest versions of file A and file C. For example, in this case, going to make a copy of file A as well as a copy of file C version 1, which is the latest version of file C. And then he's going to introduce the new feature in it. So once again, assume that Bob had asked Sundar to remove feature 2 altogether and that he wished to go back to earlier version of his working website. Guess what? Sundar can just get rid of the V2 files and only keep the V1 files. As simple as that. And if he were to fix the bug instead, he can just compare the version 1 file with version 2 file and pinpoint exactly what's going wrong by using a comparing software like Beyond Compare. However, what Sundar started to notice is that even this is not feasible because it is becoming incredibly complex to manage multiple client projects. For example, Sundar needs to rename all these files back to their original names before deploying them to the remote server. And he's also started to notice that his files are ever increasing, which is creating a problem not only in terms of organizing the files, but also it is taking a lot of space. It is at this time Sundar started to realize that it's time to let a software do the job for him. A software that will manage versions, a software that will track historical changes, create backups, and allow reversal of changes, etc. And this is the core reason why somebody, somewhere, had to come up with a software that will do this job. And that's the birth of Git. Now, Git does much more than just these, but I'm not talking about them right now because at this point in time, you don't know what is GitHub, team collaboration, branching, merging, and stuff like that. So I'm going to preserve them for upcoming lectures. And I'm pretty sure you must also be having questions like, what is GitHub, what is GitLab, what is branching, etc. Well, you just have to wait for that. I cannot fit everything under a single video. Have patience and watch the rest of the course, and you'll find answers to all the questions you might be having. But truth to be told, I like how Sundar maintains his smiley expression all throughout, no matter how his life is turning around him. Something to learn from, isn't it?
What did you just say?
No, I'm just saying that you have a great sense of fashion.
Oh, okay.
Let us see how a version control system or simply VCS software works at a very high level. Once again, assume that we have Sundar, who is a freelance developer, and Sundar has got a new client, Linda, who is a restaurant owner, and she wanted to have a website for her restaurant, so to accept online orders from her customers. And you can tell by Sundar's smile that he's ready to take up the project. But based on his past bad experiences with some of his other clients, he now have decided to use a VCS software to manage versioning. So Sundar in his local computer creates a folder with the name restaurant app, spends a few days and introduces all the files required to create a minimum functioning website. The VCS software will have its own data store to store all the historical data and backups. When I say data store, it doesn't necessarily have to be a relational database or some form of database software. It can be as simple as file system. VCS softwares typically tend to use your own file system to store the backups and historical data. As we progress through the course, you will understand this concept much better. But for now, just assume that this is some kind of a backup store to store the state of the project. Now assume that Sundar is quite happy with the progress he has made in his project. He has got a minimum functioning website and he has tested everything is working great. So he has decided to save the state of his current project, so to retrieve it back when needed. So he's going to instruct the VCS software to store the current state of the project, typically by running a command. Once he runs the command, the VCS software would essentially make a copy of all the files and store them inside the data store. Now assume that Sundar has got a new requirement to introduce feature 1, and assume that all those code changes would need to go inside file B and file C. So Sundar has made all those changes. Once again, is going to run the command to save the state of his current work. But this time the VCS software will store the information slightly different compared to how it stored earlier. This is how it's going to store. Since no changes were introduced in file A, the VCS software would only store the reference of the file A. What that means is it will just have information about the location where the file A copy is residing. And the reason for this is obvious. We don't want to unnecessarily make a copy of all the files that were untouched or unmodified and take up disk space. When it comes to file B and file C though, we have introduced new changes, but the VCS software is not going to make a copy of these files either. What it's going to store is actually the difference between the modified file and the latest version of the same file, and is going to store the same in the data store. We call each one of these as a patch set. So essentially a patch set is the difference between the original file and the latest version of the same file. And the reason for that is once again obvious. We want to save disk space as much as possible. Similarly, assume that we have new feature called feature 2, which is introduced, and file A and file B were modified. And this is how the VCS software would store the data. So we have patch sets for file A and file B, and then for file C, we're only going to store the reference of its previous version. And similarly, assume that we have another feature where we need to make modifications to file B, and this is how the VCS software would store the information. Now assume that Sundar is not happy with the version 4 of file B and that he wanted to get back to version 3 of file B. So he's going to instruct the same to the VCS software. The VCS software would then pick up the original copy of file B and then apply all the patches that came after it till version 3 to make up the version 3 file B, and is going to give back to Sundar. He can do whatever he wants to do with it. Similarly, Sundar can also write a command instructing the software to get the entire project to version 3, for instance, and the software is going to do just that. Now, obviously, there are a lot of easier softwares available in the market. We have Git, Mercurial, SVN, etc., and they all differ slightly in terms of how they manage historical data. But in general, this is how they manage historical data. Now let's dive deep and
Hold
understand
on, for
what
God's
exactly
sake.
happens. Or what happened. Why?
I don't care how it works internally. It doesn't help me with my job anyway. I just want to know how to use the software.
Oh, that makes sense. That makes sense. Just one last video and then we'll start installing the Git and get our hands dirty with a lot of practice. How about that?
Thanks.
You're welcome. Let's talk about distributed version control system. Linda is quite happy with the work done by Sundar, and she started to notice increase in her business revenue ever since she launched her website. And due to increasing customer demands, she now has decided to have even more features in her website, for which she once again approached Sundar to do the job for her. But this time, due to increasing demands from her customers, she has a very short deadline, to which Sundar has accepted the deal. But Sundar is quite aware of the fact that he cannot do this all alone and that he needed to hire a couple of folks in his team to help him deliver the project on time. So Sundar hired a couple of folks, meet Isha and Luke, who are the new members in the team. Sundar has also provided them with a brand new MacBook Pro, shared them the project files or the code, or maybe he has hosted it on an FTP server, shared the link and asked them to download. And he has also instructed them to install a VCS software on the local computer, given all its benefits. Of course, Sundar has his own local environment and his own set of problems. As they're making progress in the project, Sundar started to notice few problems with using a local version control system. Some of the problems that they were facing are these. No historical changes of other members. For example, if Isha wants to take a look at historical changes done on file A, she can only take a look at historical changes that she has done, but she doesn't have access to historical data of somebody else, for example Sundar, because she only has access to her own data store, but not Sundar's data store. Now this is clearly a problem. Unless she gets access to the entire history of changes, she cannot effectively work on a task. Another problem is it's difficult to maintain the latest code base. Whenever somebody makes a change, they need to let other developers know that they've done that change and that they need to copy that code into their local machine as well. So to have latest version of the code in all the computers. This is of course practically impossible, especially when you have multiple team members working on a single code base. And things would become even more complicated if two people happen to work on the same exact file. Another problem is no centralized management of roles or access control. For example, assume that Sundar wants to put restriction on Luke that he can only access particular set of folders in the project, but not the other folders. Well, with local version control system, he doesn't have control on that. So Sundar has thought about all these issues that they were facing and has done a research on Google and finally came up with so-called a centralized version control system, which just simply means that this time, instead of having the data store as well as the code in their local environments or on the local machines, it's going to be on a centralized server. And everybody would pick the code from the centralized server, work on it, and then send it back to the server so that others can use their code. And with this, we can get rid of all the problems we had with local version control system. Once again, if Isha wants to take a look at all the historical data of a particular file, she will easily get access to it, because this time all the patch sets are maintained in a centralized server and all the developers would have access to it. And with just a simple command, everybody would be able to get the brand new latest code and they can start working on top of it, so to avoid conflicts. And Sundar can also have better control as to who can access what. Since everything is hosted on a centralized server, he can now start to use role-based access control, and he will have control as to who can access which folders of the project, etc. However, centralized version control systems come with their own set of problems. For example, what if server goes for a toss? Or what if somebody hacks the server? Or what if Isha is having connection issues? Maybe her Wi-Fi is not working. In all these cases, developers cannot work on the project. And they might as well risk losing the entire code if they're unable to recover the server. Considering all these drawbacks of a centralized version control system, Sundar had to find out an alternative, and that's how he came across with a distributed version control system. It's basically the best of both the worlds of local VCS as well as centralized VCS, eliminating all their drawbacks. So this time with centralized version control system, instead of having one single repository, which is the centralized server, here every single developer will have their own server, and each one of the developer will have a copy of the entire history or versions of the code in their own local machine. What that means is even if the server were to go for a toss, everybody have their own local copy of the entire code as well as the historical data. And if someone like Isha were to lose connectivity, maybe because of a Wi-Fi connection, she can still make progress because she's having everything in her local computer. She can make changes, and whenever her connection comes back to normal, she can deliver the code to the centralized server so that other developers can get them and do something with it. Or in case of a data loss, every developer is having a backup of the entire code base so they can recover from it. Some of the examples of centralized version control systems are CVS, Subversion, or simply SVN, or Perforce are some of the examples of centralized version control systems. Some of the examples of distributed version control systems are Mercurial, Bazaar, and Git. Git is a distributed version control system. All the developers would have to install Git on the local machine. In addition to that, we also have GitHub, which acts like a centralized server. I think we've gained enough knowledge to start working with Git. I hope you're enjoying this tutorial. After you finish watching this tutorial, you can check the link in the description where you can get access to the entire 12-hour long course covering advanced topics of Git and GitHub without ads or distractions. You might want to go with it if you want to take your Git and GitHub skills to next level and learn them in entirety and be able to work on real-time projects or manage your own personal projects. You can either pay a nominal fee for the course or you can get free access in return for a little favor, which is only there for a limited time. Anyway, you can continue watching this tutorial and check the details later on. Okay, let us see how we can download, install, and configure Git on our local environment. Now assume that I'm a freelancer and I got a very small project which I feel I can work alone. Forget about team collaboration, forget about multiple people involving in the project, forget about GitHub for the time being, and let's just stay focused on Git. So go to Google and search for download Git. Click on the first link, but make sure that it belongs to the website git-scm. That's the official website of Git. And once you're there, depending on the operating system you're using, click on the relevant link. Now by the time you're viewing this page, you might see a different layout, but you got the point. You just have to click the link that is specific to your operating system. I'm using Windows in my case. If you're using Mac OS, there are a separate set of instructions for the same. Just follow them. And while installing, you can leave everything to their defaults and proceed with installation. And it's not necessary that you understand each and every step while installing. That's perfectly normal. In case if you have any problem installing in Mac OS X, do get in touch with us and we'll be able to help you. But since I'm using Windows, I'm going to click this. And here I basically got a couple of options. The first of which is the installer version of Git, and the other is the portable version of Git. If I download portable version, I can start using Git without having to install it. And this might come in handy, especially if I want to work on multiple computers and I don't want to install Git on each and every computer. I can just dump all these files onto a pen drive or a thumb drive and then start using Git on all those computers. But I'm going to go with installer. I'm using 64-bit OS, so I'm going to click on this. Well, for Linux and Mac users, you might already be having Git installed. You can just verify it by running a command. I'm going to show you that command in a while. or you might already be having those libraries. You just have to install them. You can refer to the installation instructions for the same. So I have this downloaded. Let's now start the installation process. If you have patience, go through this entire license. I don't have so much of patience. I just click next. Now, while installing Git, you might come across with certain steps or certain prompts or certain terminologies that doesn't sound familiar to you. And it's perfectly alright. As a rule of thumb, just remember, keep everything to their defaults and proceed with the installation. It's not necessary that you understand each and every step in this installation process. Since I have worked on Git for a long time, I understand what is being asked here. But for you, you don't have to understand everything. I would only walk you through the steps that I feel you would be able to understand based on the level of knowledge you've gained so far in this course. So I could just leave everything to their defaults, but what this prompt is basically asking us is it is asking us to choose the components that we want to install. We're going to talk about Git Bash and Git GUI in the next lecture. You can just ignore and keep rest of the stuff to their defaults. We don't want to get into too much detail. It's not worth it. Here it is basically asking you to choose a software to edit .git files. I have installed Notepad++ in my computer and I can choose that. And I would also recommend you to use the same software. It is open source. You don't have to pay anything for that. Download Notepad++. It's an amazing tool. Choose that and click next. Leave this to default because you don't know what is a branch at this point in time. So it doesn't make sense for me to explain you about this step. So I'm going to leave this to default. Okay, in this step it is basically asking us whether are we going to use git bash only or are we also going to use the command line of Windows. This step is specific to Windows. You may not be seeing similar installation steps if you're installing Git on other OS like Linux or Mac OS. You might be seeing a different set of instructions altogether. But like I said, leave everything to their defaults and finish installation. But here, if you choose this option, Git is actually going to add a path variable in system environment variables so that we can start using Git commands on Windows command processor. If you choose this option, however, it's not going to do that with an assumption that would only be using Git bash. Again, we're going to talk about Git bash, Git GUI in next lecture. Hit next. We're going to leave this to default. Basically, it is asking if you want to use the existing OpenSSH or if you already have it installed somewhere, you can just point to it. But we're going to use the OpenSSH that comes along bundled with Git. By the way, OpenSSH would essentially allow you to connect to the remote machine in a secure manner. More on it in coming lectures for sure. Leave this to default as well. Obviously, you don't understand what is commit or what is checkout, so I cannot explain you anything about this right now. Leave it to default. Leave it to default. Okay, it is talking about git pull. Again, this is too advanced for you to understand. Just leave everything to the defaults. I'm pretty sure you may not be understanding all the steps in here. Don't even try to understand. It's not necessary. We're going to explore everything in coming lectures. It's perfectly normal if you don't understand. That's perfectly all right. Trust me. Hit next. Enable file system caching. Yes, we want to. That would improve performance. We can unselect this to and hit install. Wait for a bit. All right, I don't want to read the release notes. Hit finish. Okay, we have now installed Git on our local machine. Let's go and verify if it indeed got installed. I'm going to open Windows command processor and then type in Git. So if you're able to see an output like this, that means Git was installed successfully. And the reason we're able to run git command from Windows command processor is because somewhere in the middle of the installation process, we had asked Git to include path variable of Git in Windows environment variables. Let me show you what I mean. Search for environment variables, click on Edit System Environment Variables. And if you go to path, here you would see path to Git library. So whenever you run command, something like git that we've just run, Windows OS is actually going to take a look at all these paths listed in here, and then it come across with this path where it has the code to do something with git command, and hence we're able to see this output. If you remove this, we won't be able to run any git commands from Windows command processor unless we explicitly go to this directory and do that. Anyway, if all this sounds confusing, just simply ignore. Trust me, you're going to understand everything in coming lectures. There are basically three ways we can interact with Git. We can either use Git CMD or Git Bash or Git GUI or graphical user interface. Git CMD is nothing but the Windows command processor we use to run Git commands. In fact, we had already taken a look at an example of the same in our previous lecture where we were testing the installation of Git. The other option we have is to use Git Bash, which is a tool we had installed along with Git. Git Bash is similar to Windows command processor, except that we can use standard Linux commands to interact with Git. So this will come in handy, especially if you're coming from Linux background, where you're used to running Linux commands. And now let's say that you are working from Windows operating system. You don't have to take that additional learning curve to understand Windows commands in order to interact with Git. For example, in order to list down all the files in a particular folder, inside Windows command line, you use the command dir. Whereas in Linux, you use the ls command to list down all the files. If you're using either Mac or Linux, they both come with Unix shell, and you don't have to install Git Bash. Git Bash is only meant for Windows operating system. If you're not used to either of these tools, then obviously it is always better to choose Git Bash over Git CMD. And the reason being, if you're used to Git Bash, you can also work on Linux operating system at a later point in time if you were to. The third option we have is Git GUI or graphical user interface, and as the name suggests, this tool will provide a graphical user interface to interact with Git. Now I do have to mention that Git GUI does not have support for all the features that Git has to offer. We can do more with Git Bash or Git CMD compared to Git GUI. That being said, Git GUI has its own role as well. For example, if you'd like to take a look at the overall picture, or if you'd like to get a bird's eye view of the entire historical changes, etc., then you might find it useful to use a Git GUI compared to Git Bash. However, in the rest of the course, we'd be using Git Bash as this is the best option. We might as well explore Git GUI at some point in the course, but we're going to be primarily focusing on Git Bash, which is also the popular choice. Let's take a look at some of the basic commands we can run on Git Bash to interact with the Windows file system. Now, if you're coming from either Unix or Linux background, you probably know all these commands. Feel free to skip the video. You don't have to watch the rest of the lecture. And for others, you might be wondering why do we have these commands? Well, on Windows, we create folders, take a look at what's inside it, or delete folders. We do that graphically, that Windows provides us. However, if you want to do the same from Git Bash, we need to use these commands because Git Bash doesn't come with a graphical user interface. Now you might be having another question. Why do we need to interact with the file system using these commands when we can do the same on Windows? Well, the answer is you can do it either way, but if you learn these commands, it might be helpful to you in the future. For example, if you were to work on Linux operating system, you don't have Windows OS there. You have to interact with the file system using these commands. And these commands are not difficult to learn either. They're actually pretty self-explanatory. For example, we have mkdir stands for make directory, and as the name suggests, it will help you create a directory or a folder. And then we have cd stands for change directory. It will help you change from one directory to other directory. And this is the command we use to navigate within the file system. And then we have pwd stands for present working directory, which will just print the directory on which we're currently at. So while working on git bash, if you ever wonder on which directory you're working in, then this is the command to run. And then we have ls stands for list, and this would just list down all the files in a particular directory. And this command combined with option -a would list down all the files, including all the hidden files. And then finally, we have rm stands for remove. And as you might be guessing, this will help us delete a folder or a file. Now, some of these commands would go with certain options. We'll explore them in just a while. I've created a test folder for the sake of this lecture, and this is where we're going to experiment with all those commands. First of all, let us launch git bash. You can launch git bash either from the start menu, or you can just simply right click and click on git bash here. This would launch git bash in the current directory. You're going to see a screen that looks something like this. Let us start off by creating a new folder. So guess the command that I need to use. It's mkdir stands for make directory. And I'm going to provide the name of the folder or the directory that I wanted to create. Let's call it my app or whatever. So this has created a new directory. In order to make sure that it has indeed created a directory, let us run the command ls to list down all the files in the current directory. And sure enough, we see the directory that we've just created. We can also append an option -a to list down all the files, including the hidden files. But at the moment in this directory, we don't have any hidden files to show. But this command will come in handy in future, especially when we want to explore the Git directory, which is hidden. Now let us get inside the my app directory. How do I do that? Guess the command. It's cd to change the directory. And I'm going to mention the directory. Hit enter, and we're currently inside the my app directory. To make sure that we're inside this directory, let us run the command pwd to check the present working directory, and this would print my app directory. Now let us go to the parent directory of my app. So how do I do that? We do cd space // If you want to go to grandparent directory, then you just append one more // and that will do the trick. However, I just would like to go to the parent directory. Now let's do ls command to list down all the files. Now let's say I want to delete this folder. Guess the command. It's rm and the name of the folder. But this is not going to delete the folder. Well, it doesn't delete the folder either because this user doesn't have the permission to do that, or this folder might be having files in it and it is asking us to delete those files first. Only then will it allow us to delete this folder. However, we know that this folder doesn't have any files in it, so it has to be the other reason. In order to work around this, we have to include an option along with the rm command, and that is -rf. R stands for recursive and F stands for force. Recursive would mean that we're saying not only do we want to delete this folder, but also all the files in it. And F would mean force. In other words, we want to force delete the folder regardless of the permissions. And I'm going to specify the name of the folder, and this time it does delete the folder. If we do ls now, it doesn't show that folder anymore. So take 5 to 10 minutes and try to experiment and play with these commands. Basically just try to create folders, delete folders, take a look at what's inside the folders, etc. You've probably heard of Git Commit, but what exactly is it? Let's take a look. Imagine that you're playing a video game and assume that you have made enough progress in the game that you don't want to risk losing. So you save the game at that point in time by giving a meaningful message. You continue playing the game and make some progress, and once again you feel like saving the game, and you do just that by giving a meaningful message. And if something were to go wrong with your game, you just take a look at all the list of saves you have made and load the game at a particular point. Now you need to note that the save here is not actually a backup. It is kind of like a snapshot. For example, you cannot just copy this save file and take it to another system where the same game is installed and be able to load the game from that save point. It's not possible. However, if this is a backup, you would take backup of the entire game altogether. For example, if game is inside a folder, you would just copy the entire folder, take it to another system, and start the game where you want to start. So save here is essentially like a snapshot, but not exactly a backup. Similar analogy can be explained with Windows restore points. You might be creating multiple restore points by giving a meaningful message. And if something goes wrong with your system, maybe a virus or something, I really wish that doesn't happen. But if something like that happens, you just take a look at all the list of restore points you have created, choose one of them, and restore the system back to its earlier state. And just as you have restore points for Microsoft or save option for a game, you have Git Commit for your project. So you're going to make some progress in your project. For example, let's assume you have worked on feature 1 and then you feel like you've done enough to save the project or commit the project. You do just that by using the command git commit. And then you continue with the project, you work on another feature, and then commit the project with a meaningful message. And if something goes wrong with your project, then Git will allow you to go back to earlier state of the project or revert a particular file to its earlier versions, etc. And just like save is not a backup in a game, Git commit is not actually taking a backup of your entire project, but rather taking a snapshot of your project at that particular instance of time. Assume that you have created a project with all these files, and now you feel like you've done enough to save the project or commit all the changes to the repository. Now you can't just go and run the command git commit and mention all the files that you want to commit. It doesn't work that way, unfortunately. There's an additional step involved before you commit, and there's a reason for that. For example, you could be having other files in the project which are not meant to be committed. You don't want other team members to be able to access these files. For example, you could be having some auto-generated files, or you could be having certain files which are intended only to be used locally, but shouldn't be available to outside world. And that's why we have an additional step where you need to let Git know what are all the files you want it to track. Currently, all these files in your working directory are not actually tracked by Git. You need to explicitly tell Git what are all the files you want it to track. You can do that with the command git add. You want to use this command git add and you'd mention all the files. In this case, we're going to mention file A, file B, file C, and file D, and run the command. That would essentially copy all those files into staging area. And this is when Git will start tracking these files. And once you do that, you're going to use git commit command to sort of commit all the changes to a local repository, or sometimes termed as object database. And this is not the only case where you might be needing git add before git commit. Let's take a look at one more use case. Imagine that you have a couple of features to work on, and you simultaneously worked on both the features. And assume that feature 1 changes went inside file A and file B, and feature 2 changes went in file C and file D. Now we want these two features to be going on two different commits, not in a single commit. How do we do that? If there is no concept of staging, and if we were to use the command git commit, that would commit all these changes. We don't want that. So with git add command, we'll first add all the files related to feature 1 and then we'll commit the changes with a meaningful message. Just as we have given a meaningful message while saving a game, we're also going to do the same in case of commit. Now, once you're done with that, we're going to add file C and file D and commit as feature 2. Over a period of time, we're going to maintain all such commits in our local repository. And that way, we'll be able to take a look at all the historical data. We'll be able to revert our project back to its earlier state. Or we can revert a particular file to a particular version from its past history. Or we might want to take a look at the difference between the current version of the file and its earlier versions, so on and so forth. We're going to explore all that in coming lectures for sure. And eventually, we're going to push all these changes to a centralized repository like GitHub, and that's how other team members will be able to access your changes and also all your commits and historical data. However, that's a topic of another chapter. I also should mention that when I started using Git, I joined a local GitHub community and asked them this question: why do we need to have a couple of steps to commit the changes? Why can't we just have a command that looks something like this? You're going to mention git commit -m, and then you're going to give a message, and then you're going to list down all the files that you want to commit. That might be corresponding to feature 2, for instance. Well, I didn't get any satisfactory answer from them. In fact, if you talk about other version control systems like Mercurial or Subversive, they don't have this additional step of adding the files before committing. Let us see what it means to git initialize a project. In order to understand this better, let us assume that I've got a freelancing contract where I was asked to create a web application for my client. So inside my system, I've created this folder with the name My App, inside which I'm going to introduce all the files required to create a minimal working application up and running. Now I could create all those files using the new option here, but I'm actually going to do it using git bash, just so that you'll be familiar with all those Linux commands. And the command that I need to use is called touch, and then I'm going to specify the name of the file. For simplicity, I'm just simply going to call it as 1.txt. Now obviously it doesn't make sense to have a txt file to write the source code, but we're not really interested in creating applications here. We want to learn Git, so you need to make certain assumptions. Similarly, I'm going to create 2.txt. I got the name wrong. And 3.txt. Let's rename this to 2.txt. So I've got all these files created, but currently none of these files are actually managed by Git. For instance, if I were to run the command git commit now, it's going to throw a message saying not a Git repository or any of the parent directories. So we need to let Git know that it needs to manage our project. And the way you tell it is by using a command git init. Stands for initialization. Once we git initialize the project, we're essentially asking Git to set up everything it needs to set up inside our project to now start managing our project or create versions when we ask it to. And if you notice, it has actually created a hidden folder with the name .git. This is where we have this staging area that we've talked earlier. And this is where we have the object database that we had talked earlier. In case if you're not able to see this folder, then you need to enable the option to show the hidden files and folders. Inside Windows, you need to go to the View tab, click on Options, click on Change Folder and Search Options. And once again inside the View tab, you should be able to locate that option to enable or show the hidden files. And here it is. Click on this option that says Show Hidden Files, Folders and Drives, hit Apply and OK, and you should be able to now find this folder. Let's take a look at what's inside it. Now obviously it's not really worth going deep and trying to understand everything what's inside here. We will explore some of these in the rest of the course as and when we find it appropriate. But for now, I'm just going to give you some overview as to what's inside this folder. So we have this hooks folder inside which we have a bunch of scripts. These scripts would define what needs to be done before and after a particular event. For example, we're already aware of the commit event, and then we have the script with the name pre-commit. As the name suggests, it does something prior to executing the actual commit logic. So Git might run this script prior to executing the commit logic. So we might be having things like validating the syntax, etc. If you're really curious as to what's inside these scripts, you can right click and open it up with Notepad++ and just go through all these comments and try to get a sense of what it is doing. But I don't recommend you doing it. Don't confuse yourself. And then we have the info folder inside which we have this exclude file. Let's open it up with Notepad++. If there are any files in your project that you don't want Git to consider, this is where you would list them down. You can also use patterns. For example, you can say star.log, and now Git would ignore all the files with any name but has the .log extension. Just an example. And by the way, exclude file is something that is local to your computer, and whatever you add in here is only applicable within your own repository inside your local system. If you want to have exclusions across all the team members, then there's a separate thing for that called git ignore. We'll talk about it in coming chapters. Next we have the objects folder. This is where Git would store all the historical data or the version history. And this is what we're referring to as the object database. Well, currently this folder does not have a lot of data, but once we make few commits, you're going to see this folder getting populated. You're going to see a bunch of folders getting created inside the objects folder. We have the refs folder, but let us not talk about it, because to understand this, you need to know what is a commit object, hashing, etc. So we're going to skip it for now. Config file is something we'll explore in next lecture. The description file has something to do with Git web, and since you don't know Git web, it doesn't make sense for me to talk about it right now. The head has something to do with branching, so we'll talk about it when we talk about branches. Let's move on. One thing I should also mention is that Git init is a safe operation, meaning that let's assume that I've worked on my project for a while and I've made few commits, and then accidentally assume that I run the command once again inside our project. This is not going to do any damage. Everything would remain as it is, as if we didn't run this command at all. However, if you delete this folder, then that's going to cause trouble. You're going to lose all the historical data, all the version history, etc. And then you would either need to reinitialize the project by running the git init command and start from scratch, or you need to check out the project from the centralized repository, which we'll explore in coming chapters. But as a rule of thumb, you should always remember not to mess with this folder unless you know what you're doing. The fact that it is hidden by default should tell you that it is not intended to be used by developers like you and me, but to be used by Git itself. However, there might be instances where you might need to bring some edits or do something inside this folder. For example, we've already talked about the info exclude file, where you might want to add some exclusions. But otherwise, in most of the cases, you don't want to mess with this folder. Just leave it to Git. Okay, let us see how we can configure Git credentials and try to understand its actual purpose. We now have a project initialized by Git with a bunch of files. Let us now try to run the command git commit and see what happens. Git will kindly ask you please tell me who you are. In other words, it is asking, okay, I'll commit changes for you, but who the hell are you? And it has also provided instructions as to how we can introduce ourselves to Git is by running these commands. But this is not just about you introducing yourself to Git. This is actually a real purpose of you configuring these credentials. For example, let's say that one of your team members received a defect or a bug assigned to their name, saying that one of the features is not working as expected. In the process of analyzing the problem, they're going to take a look at all the historical changes of that file. And then they come across with a change introduced earlier, which seemed to have caused the problem or which seemed to have broken a feature. Guess what? They're going to get to know the name of the person and the email address of the person who made those changes. They're going to contact them and ask them to fix the bug. But how does Git know all this? It is when you configure these credentials inside your Git. When you make a commit and push all those changes to the centralized repository, which is going to be GitHub, it will also store this information as to who has done what changes. And it includes your name as well as email address. So if you introduce good code, somebody will come back and praise you. Or if you introduce bad code, somebody will come back and blame you. In most cases, it is always the blame anyway, but no comments on that. So let us see how we can configure the credentials. And Git has already provided us how to do that. So let's use that command git config -- global. When we set this global option, what this means is these credentials are available across all the projects, all the Git projects that you create inside your system pertaining to this particular user. If you set this to system, for example, then these credentials would be available system-wide, meaning every user in the system will have all these credentials applicable. And we also have one more option that says local. That means these configs are only available for the current repository where you're working on. So first let's try with local maybe. And I'm going to first set the name. You can set any name of your choice, but it has to be your name. And I'm going to hit enter. And I'm going to set email as well. Okay, now let's take a look at where these are actually populated. So that's inside the Git folder. Remember in our earlier lecture, I mentioned that we'll talk about this config file. Well, this is where all those credentials would be set. Now let's try to set these credentials at the global level. And this time, this would be populated under users directory inside your C drive. Let me pull that up. So inside the users directory, you should be able to locate the git config, and these would get reflected over there. And similarly, if you were to set the system-wide credentials, you can do that. I don't expect your computer to be used by multiple people and they're all contributing to your work. But anyway, let's set this up. For system user though, you need to have permission. So let us launch Git from the start menu as an administrator. And then we'll be able to set the credentials. So git config, this is supposed to be system-wide changes, user name, I'm going to say and this has worked. And these would be reflected inside the program files. Let me take you there. So inside program files git etc directory, you're going to see the git config file, and this is where the credentials would be populated. And by the way, I should also mention that local credentials will override global credentials, and global credentials will override the system level credentials. So Git will try to get the local credentials first. If they're not available, it will try to search the global credentials. Otherwise, the last option would be the system credentials. If none of these are set, then obviously you're going to see an error. You can also take a look at the credentials by running a command git config list. So somewhere here you're going to see the name and email, like so. You can also give an option to see a particular level of credentials, let's say local for instance, and you can also be more specific about what information inside config you want to take a look at. You want to take a look at username for instance, and it's going to print the value of it. Let us see how we can stage and unstage the files inside Git repository. And as I had mentioned before, we need to stage files before we plan to commit them. So currently we have 3 files inside our working directory. Let us plan to commit them. Let me expand the window so that you get a better view. Also, let me type in the command clear to clear out the screen so that we get a fresh view. I'm going to do ls to list down all the files, and we currently have 3 files. If I try to do git commit now, it's going to complain us saying we have untracked files inside our project. We need to have at least one file tracked, or we need to have at least one file in staging area to be able to commit, and that's what it is complaining. Now how do we stage these files? Guess the command. Well, Git has already given us a clue. It's git add. So let's do git add, and I could just list down all the files I wanted to commit. For example, 1.txt space 2.txt, so on and so forth. This would be useful if you want to be selective as to which files you wanted to commit as part of a particular feature. However, in this case, I'd like to commit everything, so I could just use a wildcard character star. I can also use a pattern. For example, I can say star.txt, and this would stage all the files with any name that has .txt extension. So let's run this command. This is what we need. So this has now staged all our files in staging area. How do we make sure it has staged all our files? Well, there's a command to check to see the status. That's git status. So git status command will show us list of untracked files, list of files that are being tracked, files that are modified, etc. This command will come in handy to check the status of our project. As we progress in this course, you'll understand more about this command. So after running this command, our files are listed under changes to be committed, and it has also turned the color of these files to green, representing that these files are now being tracked, or these files are in staging area right now, versus in earlier case where all these files are listed under untracked files and are marked red. Now assume that I wanted to remove one of these files from staging area, maybe because I've accidentally added it in here. How do we do that? Well, Git has already given us a clue as to the command we need to run to unstage a file. That's git rm with -- cached option. Whenever I say cached or indexed or staged, we all mean the same thing. Keep that in mind. So git rm -- cached, and I'm going to list down the files that I wanted to unstage. If I want to unstage all the files, I could use a wildcard character like so, and this would unstage all the files. Let me do that. So this has unstaged all our files. To make sure that it has unstaged all our files, let's use the git status command. And as you can see, they're back to untracked files section and they're once again marked red. Let's add them back again. Let me this time try to unstage a single file, maybe 2.txt. You need to make sure that you use this option cached. If you don't use this option, then this command will have a different meaning, which we'll talk about in coming lectures. So this has unstaged 2.txt. Let us now check to see the status of our project. And as you can see, 2.txt is now listed under untracked files, whereas the other two files are listed under changes to be committed. So take a moment and try and experiment with these commands to stage and unstage the files and check the status simultaneously. Don't commit the changes just yet. We're going to talk about it in next lecture. But don't hesitate or be afraid to experiment with all these commands. You might be feeling these commands are pretty simple and straightforward at this point in time. But as we progress in this course and as I introduce more and more Git commands, you will start to feel that they're very confusing. So the only weapon you have to avoid that confused state of mind is practice. I cannot emphasize how important it is to practice all these commands. Otherwise, you'll soon confuse yourself. See you in next one. Let us see how we can commit our changes to Git repository. By the way, when I say Git repository, I could mean our project folder with .git folder, or I could also mean the object data store that we've talked earlier. It depends on the context. To avoid the confusion, I'm going to call our working directory or our project folder as Git repository. I'm going to refer to the object database as the object database, just to avoid confusion. So currently we have all these files in place. Let us make sure all these files are staged. So I'm going to do git status. We have one file which is not staged. So let's do git add 2.txt to stage it. Let's do git status once again, and we have all our files staged. I'm going to say git commit -m, and then we're going to provide a meaningful message. Why do we need to provide this message? Well, basically it describes the changes that you're committing. So at a later point in time, if you or somebody else in your team were to take a look at all the historical changes or historical commits, they get to know which commit is what by looking at its message. For example, you could be committing changes to fix a bug or add a feature. As a good practice, in real-time applications, we follow a specific format for this message. The first is going to be a combination of alphanumeric characters, which is essentially a defect or a feature ID that you pick from your defect tracking tool. If you're working for an organization, then you might be having a defect or feature tracking tool. You'd pick that ID and enter it over here. For example, it could be something like WI, some numericals. W stands for work item. It could be something else for you. And then you're going to provide a descriptive message, and even this message would be picked from the title of that defect, from the defect tracking tool. I'm going to say my working app or whatever. Let's hit enter, and all the changes that were staged would now be committed. And in order to make sure that we have all the files committed, let's do git status, and it doesn't show anything, which means we don't have any files to be committed. Now let us go ahead and make a modification in one of the existing files in our working directory. For that, I'm going to use the command echo just to fill one of the files with a text, my text in file 1, for instance, and I'm going to dump this message inside 1.txt file. This command is equivalent to opening the 1.txt file and entering the text, my text in file 1. Let me hit enter. I'm going to use the cat command to see what's inside the 1.txt, just to assure you that we have this message over there, and it prints out the text inside 1.txt. All good. Now this is a change that we've introduced. which means we need to stage this in order to commit this. So let's do git status once again, and this time it's going to say we have one file which is modified. So we need to do git add to add this file and bring it to staging area. Git status, it turned green, which means it is ready to be committed. So I'm going to once again use the commit command to commit the changes. Let's remove the defect ID for the time being, and let me just give a meaningful message. Modified file 1, for instance. Hit enter, git status, and sure enough, we have our changes committed. Now let's consider a case of deleting a file. So for that, I'm going to use the command rm, stands for remove, and then I'm going to specify the file name. Let us get rid of 2.txt, for instance. Now this command is not specific to Git. This is a typical Unix command. Hit enter. I'll do ls to see if it got deleted, and indeed it got deleted. Now this is a new change which is introduced in the project. Guess what? We need to stage it and then let the Git know that we have deleted the file, and so it gets reflected in the object database as well. So git status is going to show that file has been deleted, but this change is not staged. So git add 2.txt, git status, and we have changes which are ready to be committed. Once again, git commit with a meaningful message. This time, let me not enter any message and hit enter and see what happens. Well, Git would open up text editor that we had chosen while installing Git. In my case, it is Notepad++. For you, it might be something else. And here we enter the message which we would otherwise enter with -m option. I'm going to say deleted file 2. Save the file and simply close it, and it has committed our changes. When we used rm command, we removed the file, and then we had run git add command to stage those changes. However, we can do these two steps in one go, is by using the command git rm. So this time, instead of just rm, I'm saying git rm. This will not only remove the file, but will also stage those changes to staging area. Let's delete 3.txt, for instance. I'll do ls, and as you can see, file got deleted. But if I do git status, unlike in case of rm command, this time the changes are already staged, and you can directly commit the changes. Git commit -m deleted 3 file. Now let's take a look at all the list of commits we have made by running the command git log master. Master is the name of the branch and is also the default branch. We're going to talk about branches at later point in time, but for now just blindly run this command to see all the list of commits you've made. So the most recent one would be shown on top. As you can see, we have our first commit with my working app message, and then we modified file 1, we deleted file 2, we deleted 3 file. And I also can see the author who has done that. It is me in this case. For you, it would be whatever you've entered while configuring the credentials. When we have centralized repository and when we have a team working on a project, you'll be able to see all the list of commits done by multiple team members. And if you were to spot a commit which is causing trouble or which might be breaking a feature, you can get hold of the author by writing an email to them.
I hope you're enjoying this tutorial. After you finish watching this tutorial, you can check the link in the description where you can get access to the entire 12-hour long course,
covering advanced topics of Git and GitHub without ads or distractions. You might want to go with it if you want to take your Git and GitHub skills to next level and learn them in entirety and be able to work on real-time projects or manage your own personal projects. Anyway, you can continue watching this tutorial and check the details later on. Let's forget about Git for a second and let us try to understand what is SHA-1 hashing algorithm. The SHA-1 hashing algorithm, or sometimes referred as hash function, would take any arbitrary amount of data as input, and it's going to give us a 40-character hash code as an output. The size of the input doesn't matter. It could be as small as 1 byte, or it could be as large as 1 GB or even 1 TB. But the resulting output is always going to be a 40-character hash code. Even if the input is just one single alphabet, you're still going to see a 40-character hash code as output. And here are some of the characteristics of hash function. Same input would result in same hash code, no matter how many times you execute. If you provide the same input, that's going to result in the exact same hash code. You cannot generate data from a given hash code. Although it is possible to convert data to a hash code, it's not possible the other way. I mean, if I give you a hash code, you cannot generate data out of it. It's really difficult to find another input which results in same hash code, but it's not impossible. Well, you could have another input that might result in exact same hash code, but the probability of finding it is so rare that you don't even have to worry about it. Here is one of the use cases where hash code might be used. Whenever user registers for your website by entering the username, password, and other details, instead of storing the password in raw text format inside the database, we're going to store the hash code of that password. So that the next time user tries to log in, we're going to again run the hashing algorithm on the password that he enters, and then we're going to see if the resulting output would match with the one in the database. If they both match, then user would be authenticated and would be granted access. The benefit of storing hash code instead of storing the raw password in textual format is that if a hacker hacks your system, they get access to hash codes, but not the actual passwords. They cannot do anything using that hash code. For example, they cannot log in using that hash code on behalf of a user. Although hashing algorithm is used as a security measure, Git uses it for a different purpose, and it is to uniquely identify various objects in Git, and we're going to talk about it in next lecture. Now let's try to generate hash code from git bash using one of the git commands. So the command we need to run is git hash object, but before that, let us use the echo command with some text. I'm going to use pipe character and then say git hash object standard input. By using the pipe character, we're telling whatever is the output of this command would be the input of this command. Essentially, we're trying to get the hash code of this particular text. Let's hit enter, and we got a hash code for that text. And no matter how many times I execute the same command, we're going to see the exact same hash code. But if I make even a small little change, the resulting hash code would be entirely different from what we've just seen. For example, let's say I just added one character and hit enter. You see that these two hash codes differ significantly. You're going to understand more about hash code in coming lectures. In order to better explain how Git manages and stores the data inside the object database, I have deleted everything inside our project. So all our commits, past history, all the changes we had introduced are now gone for good. And what we have here is essentially a brand new directory. And I'm now going to launch git bash here and create a bunch of files and directories. I want to create a couple of files in this folder. So I'm going to use the command touch 1.txt and 2.txt. This has created a couple of files. In addition to this, I'm also going to introduce a subdirectory inside our project.
Guess the command to create a brand new directory. It's mkdir, stands for make directory. I'm going to name it as assets. So we have assets directory created. Let's go inside it and create bunch of files in there as well. I'm going to use the command touch one sub.txt. Sub stands for subdirectory, just for our understanding, and two sub.txt file. Let's also fill some content in these files. So I go back to the parent directory, which is our project root directory. I'm going to use the command echo text in file 1. I'm going to populate it inside 1.txt file. And similarly, we're going to populate some text inside the other files too. 2.txt. One sub. So this is going to go inside one sub.txt, which is inside the assets subdirectory. So here is our directory structure. We have assets directory and couple of files inside the root project directory, and inside assets directory we have these two files. Currently this folder is not git initialized, so let's do just that. Git init to git initialize this project, and git add all the files, git status to see the status, and as you can see, everything is staged. Now let's commit the changes. Git commit -m, my first commit. This should work. In the next lecture, we're going to understand different object types we have in Git and how all these files are stored inside the Git object database. I'll see you in the next one. Let's talk about how Git actually stores the data inside the object database. In our previous lecture, we had created a project with a bunch of files and we committed those changes. And here is the project structure we had. We have the myapp folder, which is the root project directory, inside which we have 1.txt, 2.txt, and also a subdirectory called assets. Inside the assets directory, we have one sub.txt and two sub.txt. Now let's take a look at how these files are actually stored inside the Git database, for which we need to understand various types of objects that Git has. First, we have the blob object. For each and every unique file that you commit, there's one blob object created inside the database. Each of the blob object would store the content of their corresponding file. For example, we might have a blob object created for 1.txt with all its content. Each of the blob object will also have a unique hash, and as you might have guessed, this hash would be generated using SHA-1 hashing algorithm. And the input of that algorithm would be the content of the file. Git is not really using SHA-1 algorithm to secure the application or something. It is using it to create a unique identifier for its objects. And the content that gets stored inside the blob won't be in human readable format. It would be stored in compressed format so that Git can efficiently store, manage, and retrieve it. However, Git also offers certain commands using which we'll be able to read the content inside the blob. We're going to explore that in coming lectures. Now, since there are 4 files which we had committed earlier, there are going to be 4 blobs created inside the database, along with their corresponding contents of those files. Next, we have tree object. Tree object would correspond to each and every directory in the project, including the project root directory. And just as with Blob object, tree object is also going to have a unique hash to uniquely identify a particular tree object. In addition to that, it will have references, or essentially it will maintain the hash codes of other Blob objects or tree objects or combination of both. For example, we have a couple of folders inside our project, and so there are going to be a couple of tree objects created for each one of these directories. So we will have a tree object created for the assets directory, and inside that object it will hold the references or hash code of its files. In this case, this tree object would hold the hash code of sub1.txt and sub2.txt. Essentially, these are the hashes of the blobs that corresponds to sub1.txt and sub2.txt. And then we're going to have another tree object created for the parent project directory, and it's going to have hash code of its own files. In addition to that, it will also hold the hash code of the sub tree, which corresponds to the assets directory. And of course, each one of these tree objects would have their unique hash code to uniquely identify them, so that they can be referred from some other objects. Next, we have the commit object. Once again, this will have its own unique hash, and this hash would be generated based on the commit information, like the author name, email address, the message that was entered, the time at which commit has happened, etc. And commit object would hold the reference or hash code of the parent tree. In addition to that, it will also have information about the author name, email address, the message that was typed while committing, etc. And except for the very first commit, the commit object will also hold a reference or hash code of the previous commit. You will know the significance of it in coming lectures. So for the changes that we had just committed, this is how Git would store the information in the database. So we have tree objects that corresponds to each and every directory in the project, and then we also have blob objects that corresponds to each and every file inside the project. Now it's not necessary that if you have 10 files created inside your project, we would have 10 blobs created inside the object database. It doesn't necessarily have to be that way. For example, if you have 2 files having the exact same content, and they both would generate exact same hash code, for instance, then Git will not create 2 different blob objects for that. It will just create one blob object and refer to it instead. Anyway, more on it in coming lectures. We have theoretically understood how Git actually manages and stores the data inside the object database. Now let's take a look at it practically. In order to explain things better, I'm also going to show you a graphical representation of what we're doing right now on the right hand side of the screen, so that you'll have a better picture as to what we're doing. So currently we just have one commit. Let's take a look at it. So I do git log to take a look at all the list of commits. Currently we just have one. And as you can see, we have author information, date, and even the commit message. In addition to that, we also have one 40-character hash code. Can you guess what this hash code is all about? Well, it's the hash code of the commit object corresponding to this commit. Now, how do we take a look at the content inside this commit object? Well, this hash code itself will give a clue as to how we can navigate to this commit object. Let me show you what I mean. So I'm inside the project directory. Let me enlarge it for you. I'm going to go inside the .git folder, and guess which folder we need to get into. That's objects folder. Now here we have a bunch of folders which were not existing before we committed the changes. Now if you look at the hash code and take out the first 2 characters, it says 95. We need to go inside that folder, and then you see a file with the name, which is essentially the remaining characters of the hash code. So we have 95ECE, so on. 95 is the directory name, and the rest of the characters is the name of the file. And this is what we're referring to as the commit object. If you try to take a look at the content inside it using a Notepad++, you won't be able to read it, because Git will store it in a different format that is not readable by us. The only way you can read the content in it is by running the command git cat file, and then you're going to provide the option -p, stands for pretty print, and you're going to provide the hash code of the object that you want to pretty print. I could copy the entire hash code, or I could just copy the first few characters and paste it here, and this would print what's inside the commit object. If you'd like to take a look at the type of the object, the option for that is -t to print the type, and this is commit object. Let's pretty print that object once again. So here, as I had mentioned previously, you have information about the author, committer, and even the commit message. In addition to that, we also have a hash code, which is actually the hash code of the parent tree object. So let's take a look at what's inside the tree object. Again, I'm going to use the same command to pretty print what's inside the tree object. I can just copy first few characters, paste it in here. And if you hit enter, you're going to see what's inside it. And since we have, if you go back to the root directory, we have one subdirectory and couple of files. And if you take a look at what's inside this tree object, you have couple of blobs. Each blob would correspond to individual file. In this case, it's 1.txt and 2.txt. And then it is also pointing to another tree, or it is having hash code of another tree or the subtree. So we can go inside this subtree as well. Let's do that. Guess the output. It's going to be the blobs of the two files inside the subfolder, one sub.txt and two sub.txt. And by the way, you can locate these objects inside the objects folder just as you had located the commit object. It is no different. So inside the objects folder, you will find 7a folder. So this is the subtree object we were talking about. And similarly, you can also find the blob objects. For example, let's talk about this blob. It starts with 99, so we're going to go inside that directory, and this is the blob object. Let us try to pretty print this blob object, and we should be able to see the content inside it. And once again, if you were to open it with Notepad++ or something, you won't be able to read. And you see the text that's inside this file. So that's how essentially Git stores the data inside the object database, and understanding of this is very important for you to understand all the topics we're going to discuss in coming chapters. Let's talk about blob objects and how they are managed inside Git repository. Imagine that I've created a brand new project with the following file 1.txt, and it has the following text in it, hello from Git. Now the moment I add this file onto the staging area, Git will actually try to generate a hash code out of the content of 1.txt file. And Git will then check to see if we already have any objects in object database that corresponds to this hash code. If there are none, then it would go ahead and create a blob object with all the contents of 1.txt file, of course in compressed format. Now assume that I've created one more file, say 2.txt, with the exact same text as to that of 1.txt, hello from Git. Once again, assume that I've added this file onto the staging area. Git would once again try to generate hash code out of the contents of 2.txt file. And this time, Git will notice that we already have an object that corresponds to this hash code. So Git won't create another blob object. The reason for this is quite obvious. Why would we want to create the exact same blob object when we already have one? Why don't we just use the existing one? It makes sense, right? Now let's take a look at all this in practice. For the sake of this example and to avoid any kind of confusion, I've created a new folder with the name test app, and here is where we're going to experiment and see what Git blobs can do for us. So let me launch Git bash in this folder. First things first, let's git initialize the project. And let me go ahead and create a file with some content in it. So I use the echo command. And I'm going to dump this message inside 1.txt file. So this command will not only create 1.txt file, but will also populate it with this content, hello from Git. Now let's get inside the objects directory and see how it behaves. Let me stage this file 1.txt, git add 1.txt. And the moment I do that, we see a new folder getting created inside objects directory. Guess what this file is? Well, this is the blob object for 1.txt file that we've just created. So yes, blobs are created when you stage the files, not necessarily when you commit the changes. When you commit the changes, it will create the commit object as well as the tree objects that corresponds to a bunch of blobs. In fact, that's the purpose of commit operation. It is to create a snapshot or sort of save the project at that particular instance of time. We're going to talk about snapshot in next lecture. Let's go back. Now let us see what would happen if I were to create another file with the exact same content as to that of 1.txt. So I'm going to use the same command, but this time I'm going to populate the same message in 2.txt file. Let us stage that file. I'll do git status. And we have these two files staged. But if you notice, there is no new object created for 2.txt. And I've already explained you the reason for that. Since we already have a blob object with the exact same content, Git is not going to create another object. In other words, the moment we added 2.txt onto the staging area, Git tried to generate the hash code of this content, and it has checked to see if we have any existing objects in the database that corresponds to that hash code. For 2.txt, we do have existing blob, and so it didn't create another blob. And same principle is applicable even if you were to modify a file. For example, let's say that I wanted to modify the text inside 2.txt from file 2, for instance. So we're going to replace the text inside 2.txt file, and let us stage this file. Now, can you make a guess if we're going to see a new folder getting created inside objects folder? The answer is yes, of course. So we have a new blob object created because this content right here is unique and there is no existing blob object for this. Let us also create one more file, 3.txt file with the same content as to that of 1.txt. And let's stage that file, git status, and we have these three files to be committed. So 1.txt and 3.txt are having the exact same content, while 2.txt is having a different text in it. Let's commit the changes. Well, this is not our first commit, but whatever. Let's hit enter. And as you can see, we have both commit as well as the tree object created as well, right after we committed the changes. Let's now take a look at what's inside the tree object. I'll do git log to get hold of the hash code of the commit object. Git cat file -p. Let's check what's inside this tree object. So both 1.txt as well as 3.txt should be pointing to the exact same blob object. So if you notice, both 1.txt and 3.txt are pointing to the exact same blob object, whereas for 2.txt, it's a different blob object. Now you might be having a question. Every time we add a file or modify a file and bring them to staging area, we're going to see the blob objects getting created inside the object database. And Git won't even delete them even if you were to unstage the files from the staging area. Is it efficient to do so, or is it taking up too much of space? Well, the answer is it's not completely efficient, of course. But Git has this concept of garbage collection, which happens periodically or when you run certain commands, like git pull, for instance. We're going to talk about git pull, git push commands in coming chapters for sure. But there are certain commands which will also trigger garbage collection. The concept of garbage collection is somewhat similar to garbage collection in other programming languages. For example, we have garbage collection in Java programming language, wherein all the unreferenced objects would be destroyed. And same is the case with Git. It's not 100% efficient for sure, but it also has mechanism to efficiently manage the objects. In fact, we can run the garbage collection manually. Let's do git gc. And if you notice, all the objects which were existing before are no longer existing. Now, does this mean that everything is gone for good? The answer is no. We still have all of that. For example, if we run this command, we're still going to see all that object information. And you can even read the content inside these blob objects. Now, how is this possible? We don't have those object folders, but still we're able to read those objects. Well, it's inside this pack directory. Essentially, that garbage collection operation has further compressed all those objects into a single pack file. We also have IDX or index file, and this will tell which object is located in which pack file. Currently, since our project is very small, we just have one single pack file, but as we have more and more files introduced into our project, you're going to see new pack files being introduced, and index would come into picture at that point in time. But anyway, this is not something that we really need to worry about. You can also verify what's inside the pack file. Let me launch git bash in this folder, and the command I need to use is git verify pack -v, and then I'm going to specify the name of the pack file, and this would print all the objects in it. One thing I should also mention is that technology is addictive. If we want to learn everything, sky is the limit as to how deep we can go and understand each and every concept. But is it worth it? That's the question. You don't really want to learn everything out there. It's just simply not worth it. Because we already got a lot of things to cover, and Git is only the starting point in your DevOps journey. For me as an instructor, I need to know and research about everything what Git has to offer, so that I can filter out what is needed and what is not needed for you. In fact, I'm a bit hesitant to even talk about these concepts, but I felt that understanding of this is very important to understand all the future concepts we're going to talk about in coming chapters. But otherwise, I'm a bit hesitant to talk about all these concepts which doesn't play any role in your career. I can do that if I want to. I can just teach you things just to prove that I have knowledge on that, but that doesn't make sense to you or to me. My job is to make your job easy, not complicate your job, and I would rather prefer and try my best to teach you only the stuff that are absolutely needed for your job. You need to keep that in mind and don't try to learn everything. That's one of the biggest learnings I had in my career. I just tried to learn everything. In fact, technology is very addictive. The more you explore, the more you want to know more, and it's not worth it. It's sort of like an entertainment in itself, in an odd way maybe. But it's for me. I have to take that pain, not you. Let's try and understand what is a Git snapshot. Earlier we had created a project where we had a couple of files in the root directory of the project, and then we also have subdirectory inside which we have a couple of more files. And if you could recollect from our previous lectures, this was the object structure we had when we made our first commit. Let me simplify this diagram so that it looks more compact. Now let us assume that I've introduced another file, say 3.txt, with the following text, hello from Git. And I kept this inside the root project directory. I've staged this file and then I committed the changes. Now can you visualize how the object structure would be for the second commit we make? Do you imagine something like this? So we have a new blob created for the newly introduced file. In addition to that, do you expect Git to create blobs for each and every file in the project? The answer is, of course, no. Instead, Git will create a blob for the new file, and the root tree object of the new commit will hold the hash of that new blob. And for all the other files, since they remained as is and are not modified, Git will just simply refer to their existing blobs and tree objects. In essence, the contents of the tree object in second commit would be exactly same as the contents of the tree object in our first commit, except there would be one additional entry for the newly introduced file. In addition to that, the commit object will also hold the reference or the hash code of the previous commit or its parent commit. You will know the significance of this in later chapters. So what is a snapshot here? Well, essentially every time you make a commit, you're taking a snapshot of the state of the index or the staging area at the time you make the commit. It essentially captures what every file looked like at the time you make the commit. If you were to go back in time to one of the previous commits, Git will have the ability to restore all the files in your working directory to what they were when you made the commit. How is that possible? It's because of this snapshot. Now let's see all this in practice. So I'm inside our good old My App folder. Let me go ahead and create a new file. So we have 3.txt with some text in it. Git add 3.txt, git commit, second commit. Finally, we're making a second commit. Now let us go ahead and explore the commit and tree objects. I'll do git log to take a look at all the list of commits. And by the way, talking about the parent commit, when we run this command git log, it has displayed the details about our recent commit. And then this commit object is having the details of its parent commit, which is this. And so Git will proceed and display its details as well. For this commit though, since this is the very first commit we made, it doesn't have any parent commits. And so this command will stop executing. Anyway, you'll understand more about parent commits in coming chapters. So let's go ahead and explore what's inside our recent commit. Git cat file -p, and as you can see, we have the hash code of the root tree object. In addition to that, we also have the hash code of the parent commit, which is this, and then author information, etc. Let's see what's inside this file. So here are the contents of the tree object. Let's compare it with the tree object of our first commit.
And if you notice, the hash code of the subtree object is exactly same, and even the hash code of 1.txt and 2.txt are exactly same, except for the newly introduced file 3.txt. So that explains. Let's see how we can time travel with Git. And I mean it, I'm going to prove it to you in just a while. Let's say that you worked on feature 1 and you commit all those changes as part of your very first commit. And let's assume that all those changes went inside 1.txt. And then your client says he needed another feature in his application. So you once again work on it, make another commit, and assume that all those changes went inside 2.txt file. Once again, your client comes up with a creative idea. He needed one more feature in his application. And once again, you work on that feature, make another commit, and then let's say that you've introduced 3.txt where you have all those feature 3 changes. Now let's say for some reason client has decided not to have feature 3 for whatever reason, and that he wanted to go back to previous version of his application. So how do you revert all the feature 3 changes? Well, in this example it's quite easy. You just delete 3.txt file and then you make another commit. However, as we discussed in one of our previous chapters, reverting changes is not an easy job, because in real-world applications you might be having changes scattered across multiple files, and it's really hard to revert all those changes without messing things up. You might end up breaking features which were working earlier. Fortunately with Git, we'll be able to go back to previous working copy of our project. Now I should also mention that whatever the approach I'm going to talk about to go to previous version of the project is not actually the recommended approach. The recommended approach is to use branches, which we'll talk about in next chapter. And in the next chapter you'll also understand why this is not the recommended approach to revert your changes. But for now, let's take a look at this in action. Okay, let's see how we can time travel in Git with a quick example. And once again, in order to avoid confusion, I've just cleaned up everything inside the test app folder, and we're going to do everything from scratch. Let me launch git bash. My plan is to make 3 commits, and we assume that each commit would correspond to individual features. Git initialize the project, touch 1.txt, git add. We're going to stage that file, git commit, and let's call it feature 1. We're going to repeat the process for feature 2 as well. Let's call it 2.txt, git add 2.txt, and git commit feature 2. Let's do one last commit representing feature 3. And git commit feature 3. Now let's do git log to take a look at all the list of commit objects. Let me enlarge this folder so that we can simultaneously take a look at what's happening here while we run the commands. So currently we have these 3 files. Now let us assume that I wanted to revert and go back to one of the previous versions of the project. Let's say that I wanted to go back how my project looked like when I made feature 2 commit. So the command I need to use is actually git switch. Now do take a note that this command may not be working for you if you have older versions of Git installed. So download and install the latest version of Git, only then will this command work. If you still insist to use earlier versions of Git, then there's another command called git checkout. You need to type this in. If you have the latest version installed, like in my case, then both these commands would work without any problem. However, I prefer to use
switch, and then we're going to provide the hash code of the commit where we want to revert to. Let me paste the code. You don't have to paste the entire code. The first few characters would actually suffice. Now if I hit enter, we're going to get a hint from Git saying if you want to detach head at the commit, try again with detach option. Well, whatever we're doing right now is actually called detached head state. You're going to understand about it in next chapter. And Git is also saying a branch is expected, but it got commit. Like I said before, whatever we're doing right now is not actually the recommended approach. The recommended approach is actually to use branches. Once again, we'll talk about it in next chapter. But that's what Git is even recommending. It is expecting us to use branch and not a commit. Let's proceed by including the -- detach option. And if you notice, the moment we run that command, you don't see 3.txt file anymore. And even if you were to take a look at all the list of commits by doing git log, it's going to print only 2 commits. Essentially, we just went back in time to bring back the project what it was when we made feature 2 commit. It's equivalent to I have done no changes after I made feature 2 commit. How cool is that? You can actually go to the future as well, and I'm not wrong in saying that. Let me commit the hash code of feature 3, and this time let me run git checkout instead of switch, and then I'm going to specify the hash of the third commit or feature 3 commit, and take a look at what would happen inside our working directory. Well, you see 3.txt again. We're back to the future. How cool is that? I wish there is something like this in our lives. I mean, I could just go back in time, fix things up, maybe invest in Bitcoin, and come back to the future. How cool would it be? It's only possible in Git at the moment. It's crazy, but at the same time kind of spooky, to be honest, but that's the power of Git. But anyway, do try and experiment with this feature. Just play around with it. And don't bother about terminologies like head, branch, etc. We're going to talk about all that in next chapter. And yeah, one more thing I should mention is that whenever we are switching or checking out another commit, Git was able to bring back the working directory back to what it was when we made that commit. And it has happened very quickly. The reason why it happened so quickly is because of the concept of snapshot we had discussed in one of our previous lectures. In other version control systems, what they store is actually the difference of files compared to their previous commits. And when we ask the tool to bring back the project to a certain state, it's actually going to sum up all the differences to recreate the files to what they were when we made the commit. However, in case of Git, it's all about snapshot. Basically, each and every commit object points to a snapshot or the root tree object, which has all the information of all the files residing in our working directory and all its corresponding blob objects. So it's relatively faster for Git to retrieve the content from blob objects and almost instantly or quickly load all the files onto the working directory. That's the power of storing a snapshot compared to storing the differences or patch sets like we discussed in one of our previous lectures. It's like when you're playing a game, you're going back and forth between multiple save points, somewhat similar to that. Hope it makes sense. I hope you're enjoying this tutorial. After you finish watching this tutorial, you can check the link in the description where you can get access to the entire 12-hour long course covering advanced topics of Git and GitHub without ads or distractions.
You might want to go with it if you want to take your Git and GitHub skills to next level and learn them in entirety and be able to work on real-time projects or manage your own personal projects. Anyway, you can continue watching this tutorial and check the details later on. Let us see how his life before Git branches existed, and you can tell by this image that it must be a very frustrating experience. Imagine that we have Bob, who is an investment advisor, and Sundar, who is a freelancer. Bob asks Sundar to create an application for him, and Sundar has created one application, and Bob is quite happy with how the application functions. And now Bob has decided to add few more features into his application, and Sundar has accepted to work on those features. Now assume that Sundar has started working on feature 1 and committed all those changes and has shown it to Bob. Bob is quite happy with how the feature 1 is functioning, and he has given green signal to continue working on other features. So Sundar has continued working on feature 2 as well and sent an email to Bob asking him to verify the feature. But this time Bob is quite busy with his clients, and so he hadn't got any time to check this feature. However, Sundar has decided to continue working on other features because if he keeps waiting for Bob's reply, he might not be able to meet the project deadline. So he delivered feature 3 and feature 4 as well and has sent an email to Bob asking him to verify all these features. Bob verified all the features, and for some reason Bob is not happy with feature 2 and that he has decided to eliminate that feature altogether from his application. So Sundar thought about it a bit and he realized that it's really difficult to undo all those changes. Because if he tries to undo all these changes, he might end up breaking some of the features which were working. Another thing that Sundar thought of doing is to go back to one of the previous versions of the project by running the command git switch or git checkout. But the problem with it is Sundar will not only get rid of feature 2 changes, but he will also get rid of feature 3 and feature 4 changes, which were working fine, and Bob is quite happy with these features. This is just the tip of the iceberg as to the kind of problems we might face when we don't use branches. For example, in real-world applications, you might not be the only person who would be working on the application. You might have the code base and the list of commit histories residing on a centralized repository, and multiple team members, and could be from multiple teams, would be contributing to that project. Everybody would make their own commits, introducing their own features. Now you cannot risk going back to one of the previous versions and risk losing all the team's effort. Another problem you might face without branches is when you were to work on multiple features simultaneously. Let me explain you what I mean. Assume that you are assigned with all these features and you have to finish them before a deadline. Let's call them feature F1, F2, F3 and F4. While it's not recommended that you multitask, sometimes your situation might demand you to work on multiple things simultaneously. For example, assume that you started working on feature F1, made some changes related to F1 inside your working directory, and then you have to write an email to somebody, and based on what they reply, you'd want to continue with feature 1. While you wait for the reply, you're not expected to watch YouTube or something. Your boss would expect you to take up another task, maybe start working on feature 2 for instance. So you pick up feature 2 and start working on it, introduce code related to feature 2, and then let's say that you're dependent on somebody else for feature 2 as well, and you have to wait for the reply. So you take up feature 3 as well. And while you're managing all these features, waiting for replies and updating the code accordingly, your boss would ask you to send an update on feature 4. You would tell your boss it is in progress even though you haven't started on feature 4. Just to keep him happy, you might tell him it is in progress. So you're kind of forced to start working on feature 4 now. And then suddenly you get a reply for feature 1. Or someone in your team asks you to deliver feature 3 because they're dependent on them. I hope you're getting where this is leading to. When you have all these partial changes of all the features inside your project, this would lead to a lot of mess and a lot of frustration. Let's talk about one more realistic problem that you might face if you don't use branches. Imagine that you have centralized repository where all the team members would be contributing to the code base. And there comes this new lady who just joined the team. She didn't have any experience in programming. She just graduated out of college and joined the organization, and she was assigned with a feature to work on. While she's working on the feature, she felt like there are too many changes to commit. So she thought of making a partial commit onto the code base. So she commits those changes, and obviously, as you can expect, this is not an ideal thing to do. But she's new to the team, she doesn't know a lot of things, she is still learning, and she made a partial commit. And rest of the team members would start taking those new changes because they need to get the latest code to start working on their own features on top of the existing code. And they contribute to the project, introducing their own set of changes and introducing new features or bug fixes. Now, because of that partial commit done by this young lady, all the future commits might actually break as well. Or even worse, it might actually break things which were working fine earlier. Now, it's understandable that she is new to the team and she is bound to make mistakes. But how about all the senior members in the team who did a fair job, but yet they have to take the blame because their code is not working as expected due to the changes introduced by this young lady? Now, this is just a consequence of mistake done by one team member. How about multiple team members introducing all those half-cooked ideas onto the main code base? It will soon become a nightmare. It will soon become hard to manage, not being able to meet the project deadlines, too many issues to fix, etc.
So, I guess I now need to learn about Git branches?
Absolutely.
Then, what are you waiting for? Teach me those stuff, damn it.
Okay, easy Sundar. That's the plan. That's why I'm here. I'm here to teach you things.
Thanks.
You're welcome. Okay, let us try to get some idea as to what are Git branches. Now, I do have to mention that with this video alone, you may not be able to understand or get complete picture as to what Git branches are. You need to watch all the rest of the lectures in this chapter in order to have a complete picture of what are Git branches, what is their purpose, why they existed, and how they solve all the problems we had talked earlier. So let's move on and try to get a zest of what are Git branches. Git branches is such an important feature in Git that even the Git logo itself is having a symbol representing Git branches. So you can understand the significance of this feature in Git. Now I want to ask you a question. What is the first thing that comes to your mind when you hear the word branch? Would you imagine something like this? Well, you're not wrong. Here, if you observe, we have a main branch, and then we also have sub-branches which come from the main branch. And each one of these branches are having their own set of leaves. Well, this is synonymous to what branches are in Git as well. So in Git, you might have a master branch created by Git when you initialize the project and make your first commit. We don't have to manually create this. Git has done that for us. And all the commits that we've done so far went inside this default branch, master branch, even though we're not aware of it. And then we could also have feature branches that come from the master branch. Just as we have main branch and sub branches in a real world branch, we also have master branch and feature branches in Git. And just as each of the branches would have their own set of leaves, even in Git, we have commits residing in each one of these branches. And all these branches would evolve independently. For example, if you make a commit in feature 1 branch, those changes will not be available in any of the other branches. And same is the case with other branches. If you make a commit in master branch, then those changes will not be available in other branches. If you want to make a commit in a certain branch, you need to first switch to that branch and make a commit in that branch. And those committed changes will not be available in other branches. And when you switch to a branch, Git will make the working directory look like what it looked like when you made the last commit in that particular branch. Eventually, the goal of all these feature branches, in most cases, would be to get merged in the master branch, which means we will now have all the changes introduced in these feature branches inside the master branch. Now obviously this may not be making complete sense to you at this point in time. So let's break it down and see how this project might have evolved from the beginning. So when you initialize the project and make your first commit, you have a master branch created by Git. And let's say that you have made a couple of commits. And these commits would go inside the master branch. So we have the first commit, which does not have any parent. And then you have the second commit, which has the first commit as its parent commit. And now let's say that you are assigned to work on feature 1. Instead of committing all those feature 1 changes inside the master branch, what you're going to do is you're going to run a command to create a feature branch. And this would just create the feature branch. And once you do that, you need to switch to that branch to be able to make commits in that feature branch. So you would run a command to switch to that branch. And once you do that, you're going to start introducing all the feature 1 changes. When you make the first commit, we have a commit object whose parent would be the last commit of the branch from where you created this branch. In this case, it's the master branch. So the first commit that you made inside the feature 1 branch would now point to the last commit of the master branch. And then let's say that you have made a couple of commits inside the feature branch, and none of the changes that you've introduced in feature 1 branch would be available in master branch. Because as I had mentioned before, all these branches would evolve independent to each other. Now let's say that you have decided to work on something else and you wanted to contribute all those changes inside the master branch. So you would again switch to master branch and make a commit. Do take a note that these two commits are having the exact same parent. And whatever the changes that you've introduced with this new commit inside the master branch will not be available inside the feature branch. So feature 1 branch would only have all the changes introduced in master branch till the time you created feature 1 branch and made the first commit, plus all the changes that you've introduced in feature 1. Okay, let's say that you have made one more commit inside the master branch, and it is at this point in time, let's say that you were asked to work on feature 2. Guess what? You're going to create yet another branch, let's call it feature 2 branch, and then you have to switch to that branch to be able to make commits inside the feature 2 branch. You're going to make a commit, and this time it would be tracked inside feature 2 branch, and this commit object would be pointing to the last commit of the master branch, because it is the master branch from where we have created this feature 2 branch. And all the subsequent commits you're going to make would be tracked inside feature 2 branch. Now once again, you might want to go back to master branch and make bunch of commits. And not to mention, feature 2 branch will have changes that you've introduced in master branch till the time you created feature 2 branch and made the first commit, and all the commits that you've introduced in feature 2 branch, but does not have any of the changes that you've introduced in any of the other branches, like for example feature 1 branch. Eventually, you want to merge all the changes that you've introduced in these feature branches into the master branch so that you have all the changes inside the master branch. Now, obviously, you might be having a lot of questions as to how this would solve all the problems we had talked earlier. And what exactly is branch? How does it work internally? And how is it managed? What it means to when you switch to a different branch? You're going to find answers to all such questions in next few lectures. And by the way, I've mentioned that we make commits inside the master branch. Typically, we do not tend to make commits directly inside the master branch. We always create a new branch, be it a feature or a bug fix. And then once we're sure of all the changes, once we test them, get them reviewed, only then will we merge all those changes inside the master branch. So essentially what master branch would have is so-called a merge commit. We'll talk about merge commits in upcoming lectures. I don't want to talk about it right now and confuse you further. I'll see you in next one. Okay, so far we have some idea about branches. Now let's take a look at how branches solve the problems that we had talked earlier. Let's talk about them one by one. Imagine that you are asked to work on multiple features simultaneously. This time, you're going to have multiple branches, each corresponding to individual feature. It's very easy for you to multitask because let's say that you wanted to work on feature 1. You're just simply going to switch to that branch and continue working on feature 1. And somewhere in the middle of your work, you might have decided to work on another feature, say feature 2. Maybe because you're waiting for an email reply or whatsoever. So guess what? You're going to switch to feature 2 branch and continue working on feature 2. And since code changes introduced in one branch will not have any impact on the other branches, there's no chance that you would confuse yourself with code changes introduced for multiple features. We have a separate context for each and every feature, and they evolve independent to each other. So branches have sort of solved the problem of you not being able to multitask between multiple features. Now assume that some inexperienced programmer joined the team. Guess what? They can just create a branch, experiment everything that they wanted to experiment, make mistakes, learn from those mistakes, and bring updates. Finally, when they're ready with the changes, and once after they test all those changes, senior members in the team can actually review all the code changes, and only then will they accept all those changes to be merged with the mainstream of development. So there's no scope of one member in the team messing with the code and costing others work as well. Now let's say that you wanted to get rid of one of the features. Then you don't have to take the effort of undoing all the changes and risk creating problems. Or you don't have to go back to one of the previous commits and risk losing all the team's effort that came after it. Instead, you can just simply delete the branch and you get rid of the feature that you don't want. It will not have any kind of impact or influence on others' work. One another advantage with branches is that you can make partial commits. Without branches, if you make partial commits, you might risk introducing new bugs in your application or breaking some of the working features. However, with branches, you can make multiple partial commits, especially if your feature is very big. And once you're done, you're just simply going to merge all those changes onto the master branch. Hope it makes sense. Okay, let us try and understand how branches would work. But before that, let us understand what exactly is a branch. If I were to define a branch would simply be a reference to a commit. Or in other words, is just a pointer to a specific commit. Now you might be wondering how come something as simple as this can do so much for us. It does. Let me explain you what I mean. Let's say that I've just initialized the project using git init command. And since branch is a reference to a particular commit, we need at least one commit to have a branch. And that's why you're not seeing anything right now. A branch would be created the first time we make a commit. And that branch is the master branch, which would be created by Git itself. We don't have to do that manually. You can think of it as simply a file with the name master, whose content is going to be the hash code of a specific commit. And a branch always points to the last commit on that branch. Currently we just have one single commit, so this master branch would point to that commit. Now let's say I made a new commit, then the branch would now point to that new commit, so on and so forth. I make a new commit and branch would point to that new commit. Now let's say that I have to work on feature 1. We're going to run a command to create another branch. Let's call it feature 1 branch. The moment you run that command, Git will create a new branch, essentially a new file with the name feature 1, whose content would be the hash code of a specific commit. What commit would it be? Can you make a guess? Well, it would be last commit of the branch from where we have created feature 1 branch. So it would point to this commit. Now let's say that I've made a couple of more commits. Where do you think those commits would go into? Well, it would go into master because this is the current active branch. So those two commits would go inside the master branch, and as you can guess, master would now point to that very recent commit in that particular branch. Now let's say that you wanted to make some commits inside feature branch. Well, you have to run a command to switch to that branch, and once you do that, all the commits you're going to make would be tracked inside the feature 1 branch. If I make a commit now, how do you think the diagram would look like? Well, a branch would always point to the last commit on that branch. So feature1 branch would now point to this new commit, and this new commit will have the master branch commit as its parent. So it is at this time we will have two commits having the exact same parent. Now let's say that I made a couple of more commits. Where do you think those commits would be tracked? Well, since feature1 branch is the current active branch, those commits would be going inside the feature1 branch, and of course feature1 branch would now point to the last commit on that branch. Now a question to you. Imagine that I've added one file in each one of these commits. Now if I were to look at the working directory, what are all the files you're going to see? Can you guess? Well, every time you switch to a branch, Git will rewrite the working directory to look like what it looked like when you made the most recent commit on that branch that you just switched to. So in this case, the current active branch is feature1 branch. So you're going to see all these files A, B, C, and F, G, H. You're not going to see files D and E. And now if you were to switch to master branch, you're going to see A, B, C, D, E files, but not F, G, H files. Hope it makes sense. I'll see you next one. Okay, let us see branches in action with a quick example. Once again, I've created a new folder, my app, and this is where we're going to experiment everything about branches. So I'm going to launch git bash here. Let me create one file, commit it under master branch, and we're going to start from there. I'm going to git initialize the project and then touch 1.txt to create that file, git add 1.txt to stage that file. And before I commit the changes, let me take you to git refs heads directory. This is where Git would create list of branches. Let me go back to git bash and let me commit this change. Git commit -m. First commit in master branch. The moment I commit these changes, you're going to see a new file being created by Git. Let's take a look at what's inside this file. Do take a note of the name of the file. It's the name of the branch, the default branch that Git has created for us. It's master, and the hash code is the hash code of the commit that we've just done. So if I go back to git bash and do git log, the hash code that you see here is exactly the hash code that you see inside the master file. So essentially, the branch master is pointing to this particular commit at the moment. Let's make one more commit and see what's going to happen. Touch 2.txt file, git add 2.txt, and then once again let us commit the change. Let's call it second commit in master branch. And let's take a look at the content inside the master file. So cat.git refs heads and then the file master. And as you can see, master is now pointing to the last commit in this current branch. So if I do git log, you're going to see that the master branch is actually pointing to the very recent commit that we've done. Now let's try to create a new branch. And the command for that is git branch, and then you're going to specify the name of the branch that you want to create. Let's call it feature1. So this has created feature1 branch, but we're still on master branch, and you can tell it by looking here. It says master, so we're currently in master branch. If I make a commit right now, that commit will not be available in feature1 branch. But if you notice, Git has also created another file inside the heads directory with the name feature1.
and guess the content inside it. Well, it would be the hash code of the last commit of branch from where we created feature 1 branch. So essentially, if you take a look at the content of feature 1 file, it's going to point to the last commit of the master branch as expected. Now if I make a new commit, where do you think the changes would go into? It would be inside the master branch because that's the current active branch. So let me make a commit, touch 3.txt, git add 3.txt, and we're going to make a third commit inside master branch. If I do ls, you're going to see all those 3 files. But if I switch to feature 1 branch, so I do git switch and the name of the branch I want to switch to, feature 1. You can also use the command git checkout and the name of the branch. Either way. As you can see, we have switched to feature 1 branch. You can also tell it by looking here. Now can you guess what are all the files we would be seeing if I do ls? Well, we should only be able to see 1.txt and 2.txt and not 3.txt because 3.txt is created in master branch after we created this feature branch. As you can see, we're only seeing 1.txt and 2.txt files, which is expected. Now since we're inside the feature 1 branch, all the commits I'm going to make now would be tracked inside feature 1 branch. So let's do one commit. I'm going to create one file, touch, let's call it feature 1 3.txt file. I'm naming like this just so that we know that this belongs to feature 1 branch for the time being. Git add, we're going to stage that file, git commit -m, adding feature 1 3 file in feature 1 branch, whatever. So we made the commit. If I do ls now, you're going to see all these files. Let me go back. So in the working directory, you're going to see all these files. Now let's take a look at what would happen if I were to switch to master branch. So I use git switch command, or I could also use git checkout and then the name of the branch. The moment I do that, you can see Git has updated the working directory that suits master branch. So Git is aware of the snapshot of the latest commit done in master branch, and it's going to make the working directory look like how it looked like when we made the last commit in master branch. And if I were to switch back to feature branch once again, you're going to see the working directory getting updated accordingly. We don't see 3.txt. And feature branch would now point to the last commit done in that branch. So if you take a look at the content of feature 1 branch, the hash code is now updated, pointing to the latest commit in feature 1 branch. If you do git log, you would see that that's the latest commit done in that branch. Now it's really crucial for you to understand how exactly is this working. I want you to experiment with this. Create files on multiple branches, switch between multiple branches, and try to understand how Git behaves with branches. If you do not practice, it's almost certain that you will confuse yourself pretty soon. So do not hesitate to practice. You feel like you're knowing everything, but when you actually practice, you might have surprises. So don't hesitate to experiment with this. Take some time and practice what I've just taught, and make sure that you're comfortable with branches. What you just watched is just the beginning, like maybe 5 to 10% of what you ideally have to learn. And we haven't even touched on GitHub, which is the centralized code repository that a lot of organizations rely on.
There are a host of other topics like rebasing, stashing, merging, forking, pulling, contributing to open source repositories, branching strategies, digital signatures, GitHub administration concepts, development lifecycle, etc. You can learn all of them as a 12-hour long course without ads or distractions. Check the details in the description below. Also, if you want to know the complete learning path of Git and GitHub, you can check my other video on YouTube, which briefly talks about the same. Link is in the description. Thank you for watching, and I hope you really enjoyed as much as I did making it. If you did, do like, subscribe, and check my other courses as well. I'll see you soon. Thank you.